Thank you for having me. My name is Kate Boden. I'm a PhD student at CU Boulder. I work with Professor Ian Grooms, and I want to talk about the effects of backscatter parameterization in a global ocean model on ensemble-based data assimilation. So we've talked a little bit already today about the motivation for data assimilation in ocean modeling. I want to emphasize that I'm using a low resolution model, and for low resolution models, we definitely want to improve subseasonal to decadal predictions with accurate initial conditions. And as we all know, data assimilation is a great method to constrain the initial state using real observations. So I have a little cartoon in the bottom here. On the left, we're initializing 3 ensemble members at time t0, forecasting forward in time to our prediction time, and we see large uncertainty at time t star. But if we initialize with data assimilation, here my observations are made available by seals, then our constrained state, represented in green, has a reduced uncertainty at t star compared to the unconstrained state. If we're using the ensemble Kalman filter, here's another cartoon kind of demonstrating what the Kalman filter is doing. And so what I want to emphasize here is this is a well-behaved ensemble Kalman filter where at time t3, after we've done 3 assimilation cycles with our observations in orange, we see that the ensemble is pretty close to the truth, much better than if we had run the dynamics freely, assuming that there is some chaotic dynamic behavior in our system. If I move forward here, though, to an undispersed ensemble, and I'm actually going to move back and forth quickly here. Hopefully what you're seeing is the reduction in the spread in the forecast. So the forecast in blue here is a lot smaller in the underdispersed case. And then what this can lead to is by time t3, we're no longer even updating our ensemble, even though a good observation is being made available to us. And this would be the most extreme case, like full ensemble collapse, where there would be no variance in the system and all your ensemble members would be just 1. That's just not really shown here, but humor me to say that there's no variance in the system. And so your update to the state here, delta x, with your Kalman gain, if the sigma x squared goes to 0, then you wouldn't update your state at all. So we get filter divergence. Why does this happen? Well, 2 reasons that I'm going to talk about. We have model errors and we have filter sampling errors. So as I mentioned earlier, I'm using a coarse resolution model, and with those models of the ocean, we're not resolving subgrid scale processes, which are adding a lot of variability into the real ocean. And so with the filter sampling errors, we have finite ensemble sizes, and we're relying on those finite ensembles to estimate our mean and covariance structure. So we know that we get spurious correlations and underestimated covariance. Current solutions for dealing with this, though, is you can kind of just do it from a filter perspective. So both model errors and filter errors can be fixed through the filter using localization to deal with spurious correlations, and then inflations to inflate the ensemble covariance. I'm going to focus on inflation because that is what I'm hoping to address with a new parameterization in a coarse resolution ocean model. And adaptive inflation is a clever algorithm that looks at the difference between the observation and the ensemble mean. And if that difference is much greater than the combined variance, then you apply an inflation factor. And it's adaptive both in space and time. So I'm showing you January 10th inflation factors globally, and then March 11th inflation factors. And we started our model on January 1st, and there was a lot of bias in the initial ensemble. So we see large inflation factors because the difference between the observation and our biased ensemble mean was large. And so we get these like hot pink zones, especially this is along like the tau array here. But then, 2 months later, we've done data assimilation. We know data assimilation is an effective method of removing bias. And so we've reduced that bias and thus reduced the difference between the ensemble mean and the observation so that they can be explained by the combined variance. This is an effective method and it's used in a lot of ensemble-based data assimilation, but it doesn't really address the underlying issue of the lack of model variability. So inflation is useful in coarse resolution models to add variability to the ensemble so we don't get that ensemble collapse, but in the mesoscale eddies that are really leading to the variability in the ocean, maybe we can just improve the parameterization of them in these coarse resolution models. So I like this image here from the Met Office that shows you the difference between a 1 degree eddy parameterized model and what you can see. And then you get much more variability if you go down to the 1/4 degree eddy permitting, and then, you know, the greatest variability, and you're really starting to get at what the real ocean looks like at these finer resolution models. But the model I'm going to run is going to be in 2/3 degree. And so I want to still try to capture some of that variability with a better parameterization. And the hope is that that will also improve the ensemble data assimilation by not having the under dispersed ensembles. So new solutions for our model errors and our filter errors. What if we could have a higher resolution model, but what if we keep the coarse resolution model, because we're doing this at a global scale, and instead we improve the parameterization. So the model that I'm using is the Modular Ocean Model 6. This is actually a pretty fine resolution picture. I think it's salinity, and so it's at 1/8 of a degree, but again, I'm running it at 2/3 degree. And then I'm gonna do the data assimilation using DART, the Data Assimilation Research Testbed, ENKF. DART works with a 2-step update where you first look at the observation in observation space. So you increment there and you get the blue PDF, and then you do a regression back to state space, and that's your update. But what's important for us here is what's the actual backscatter parameterizations that we're adding. We have 2 stochastic ones and 1 deterministic. If you run MOM6, these are on by default. So when I ran a control case, I would turn them off. And they're active in different areas of the ocean. But what's important is that these parameterizations are going to improve variability in our model. And there's other papers that have already shown that. But what I would like to do is to examine what extent the physically based backscatter parameterizations within MOM6 can potentially reduce or replace the need for covariance inflation in ensemble data assimilation. Because although effective, it would be nice to get at the root cause of why we even need these inflation to begin with. So I set up an Aussie. So I have a truth run. I'm running this for 2011. I have synthetic observations of salinity and temperature. I interpolated them onto the World Ocean Database Grid to give it some realistic spatial and temporal component. And then I have 40-member ensemble, 5-day assimilation window, and then I'm going to show you some of our preliminary results. So this is a work in progress, but we do have some fun results to share. The 4 experiments that I'm going to run, since I have 2 types of observing sources, I have a control where there's no backscatter, and then I have a backscatter case. I'm going to run a control with a control and a backscatter with a backscatter. This is my ensemble, is either a control ensemble or a backscatter ensemble. And then experiments 2 and 3, these are like the cross experiments, but I'm highlighting in green 1 and 4 because we're just going to focus on those results today. And all of our results are going to be for sea surface temperature to also keep things focused. Okay, hopefully it'll go away. So here we're looking at bias, the difference between the ensemble mean and the truth. We have the control on the left, and backpack is a shorthand for backscatter package. So I'll use that moving forward. And I like these images because we're just doing 1 month of January. We start with a lot of bias in the system, represented by the strong colors. And then on January 5th, that's our first assimilation cycle, you see that big reduction in bias. So both of them are certainly reducing the bias and able to deal with the initial ensemble. Maybe there's a little more bias in backpack, but what I kind of want to focus on with this is the inflation factors. So in order to, I have adaptive inflation on, so this means that the inflation factors are going to change based on how far the observation is from the ensemble mean and whether or not that's explained by the combined variance or covariance in the higher dimensional case. So we have the control on the left, and you can actually kind of see where the observations are based on where the inflation factors are large. And for the control, it certainly is a lot larger than it is for the backscatter case. And that's just because we need more inflation to add more variability into our control simulation. However, if you look at I just showed you January because that's when we have a lot of bias that we need to correct for. But once that's corrected for, it looks kind of like a wash to me, the difference between the control and the backpack. Certainly here in the Pacific, you're seeing larger inflation factors than you are with backpack, but backpack has more of, larger inflation factors off the coast of Africa and the Atlantic here, and smaller over here, but maybe you have this, it's different how it's performing. Not necessarily that we totally got rid of the need for inflation. Here I can also show you the RMSE. We often like to look at RMSE as a measure of success for an Aussie. I'm showing you horizontally averaged across the ocean, and then we have time, so these are different months on the x-axis, and then depth on the y-axis. And you can see in red, here's that initial bias. You see it in both of them. And then assimilation starts to remove that bias. You can actually see the assimilation window, which is kind of cool in the backpack case. But certainly the control is doing better. The blue colors indicate lower RMSE, warmer colors indicate higher RMSE. So backpack has much higher RMSE. However, maybe that's not necessarily a measure of of whether or not which simulation is actually giving us a realistic model of the ocean. And to kind of demonstrate that, we've been doing a literature review this week and looking at two different papers. Here, one where they start to reduce the scale of the model, and they find that they're getting worse predictive skill. And then in this model, in this paper, just a few years later, they start to say that the gap between observation resolution and model resolution is a key contributor to the lack of predictive skill in these high resolution models. So it's kind of, even though we're not changing the resolution of our model, we are changing the parameterization to increase variability. And I didn't mention earlier, but we had 250,000 observations, and that's globally. So it's pretty sparse observing system. And then we're comparing that to, a finer model resolution, in the sense that effective resolution is better by having these improved backscatter parameterizations. So we kind of have hope that RMSE is not necessarily telling us the full story here. And to kind of demonstrate that, I'm going to show you videos of sea surface temperature. We have the control on the left, backscatter on the right. And when I showed this in an ocean model working group, and there's a lot of great ocean people here too, so I would be curious what you think. When they looked at the Pacific in particular, this is looking better, more realistic to the type of variability we expect in SST across time. And so, you have this smooth, nice looking field on the left, but that's not necessarily realistic to what the actual ocean is doing. So the RMSE looks really good because the difference between my control observations and my control ensemble mean is small, but it's not necessarily realistic. So we do think that there's improvements to be had with using improved parameterizations, backscatter parameterizations that are both stochastic and deterministic. The final thing I want to mention is correlation structure. So as you might expect, especially from that last video, the control has a much larger correlation than backpack does. So we see a much smoother field. And so from the observation here, given by the yellow star, when we're doing the ENKF update and we're relying on that correlation structure, then we're probably doing a pretty good job if we're staying within that radius. So the green dashed line is my cutoff. And so DART uses a cutoff for your localization radius. And then outside here, everything kind of looks like noise. So you wouldn't want to update based on that observation. But in the case of backpack, if you use the same localization, then you would probably be updating a lot of spurious correlation based on a lot of spurious correlations, which is going to decrease your performance. And we actually saw that when we initially tried to run the simulations with the same cutoff. So a recommendation would be, if you have stochastic backscatter or even deterministic backscatter, maybe reducing your radius. But also we kind of want to compare this to real data sets about the correlation structure for spatial correlation structure for temperature. And this is probably, we might expect to be a better representation of reality, which is again, advocating for the use of these types of parameterizations in coarse resolution models and trying to deal with how that interacts with data assimilation and observations. Okay, I want to finally thank all the people that made this project possible. It certainly, getting Mom6 and DART to play nicely with each other is a challenge unto itself, and it wouldn't be possible without my advisor, Ian, and then all the DART team, Mohad, Jeff, Dan, Helen, Kevin, and Molly. So thank you to everybody that contributed to this.
Thank you, Kate, for the wonderful presentation. And while our one question by Dan. So do you think the blobby structure of the inflation in the tropical Pacific could cause any issue? And do you get zero inflation where there are no observations?
The blobby structure in the Pacific.
Yeah, the Pacific, in the tropical Pacific. Yeah.
Like these things. Well, I guess these make sense to me in here. Maybe I should play it so that we can see it nice and big. I guess the blobby structure, like inflation is only going to influence around the observation. So it actually makes sense to me. You also see here, this is where I expect a lot of observations come online at some point throughout the year. And should we expect the inflation factors to be 0? I guess I haven't seen that, because here you can say 0 is like a black. Well, actually, no. On a day-to-day scale, when I look at these results, because the adaptive inflation is following the algorithm, I'm not personally in charge of picking the inflation factors, and I've seen like in these regions very low inflation factors. But yeah, that's actually I don't know when I would expect it to be 0.
Okay, thanks. And another question from Lars Neger. Did you consider to CRPS to assess the scale of the assimilation? So given that the RMSE might not tell the whole story.
Right. Yeah. We haven't looked at that yet. No. We kind of want to look at the correlation structure has been like what's interested us recently. But yeah, spread and yeah, looking at like a CRPS could be an interesting other step to do. Like, are we capturing the variance? I guess I did let's see. I did do a plot like this where I'm comparing the RMSE to the spread in the ensemble, and so we would expect them. It does, like, we're still under dispersed in both cases. Blue here is backpack, and orange is the control. And you can really see the DA cycle here. But it would be cool. I think that's a nice suggestion to look at the CRPS.
Yeah. So yeah, thanks. And personally, I also have a question. So you mentioned the statistical parameterization compared to the deterministic parameterization, because currently I'm also play a little bit around with the parameterization thing. So how did you consider the uncertainty when you define these stochastic realizations for the parameterization?
Do you mean the uncertainty in the synthetic observations, or?
Yeah.
So, yeah, go ahead.
Because I'm also testing with the synthetic experiments, so I'm just wondering how you design this whole experiment, maybe just in a few words.
Yeah, sure. So for designing the experiment, DART is really the magic behind it all, because you can set up synthetic observations. They have programs that do that. And so my understanding of the error in the temperature and salinity is that it's 0.25 for temperature, and it's kind of, that's just what they're adding. So for like, you're going to have more variability in the synthetic observations from the backscatter case, because there's just more variability in that model to begin with. But then you're going to add the same like delta t for the error to both.
Well, I mean, for the
my interpretation, I'm running the same. Sorry, say that again.
Yeah, I'm sorry for the interruption. I mean, for the parameterization, not for the observation. I mean, for the parameterization, how do you consider these uncertainties?
I guess maybe I'm not fully understanding, but like the parameterization, so in the model itself you're talking about?
Yeah, in the model itself.
Because I'm just measuring uncertainty as like a measure of spread, because I assume the backpack is truth, that there is, that is my when I run it as a nature run, that's my truth.
Okay, I understand. You add errors to your truth. Okay, so that's
Exactly. I add errors to my truth, and that's my synthetic obs. Does that make, did that get it?
Yeah, okay, then I understand how, yeah, that's a little bit different from what I'm wondering. Of course, we are working on different components, but anyway, thank you. Okay,
Okay.
yeah.